So a very complicated summation over here, which reduces to a very simple result. The question is, can you show that that is true? And the hint here is to look at these two generating functions and then take their product. So pause the video and see if this is a successful strategy to show that this thing reduces to 1. Let's try. Let's just write down our generating function j xt, so gxt rather, exponential x over 2, and then t minus 1 over t. And we know, by definition almost, that this is the sum of n going from minus infinity to plus infinity. We have the Laurent series here, where the coefficients are our friends, the Bessel functions. Okay, so this we know. Let's now make the suggested substitution t, replace that by minus t. So now we have exponential x over 2, and then we have minus t plus 1 over t. Now, if we do the same thing on the right-hand side, summation minus infinity to plus infinity. Now, since we're going to take the product of these two guys later on, we can already now make sure that they have different indices. Otherwise, we run into problems. So we have jm of x, and then replacing t by minus t, we have minus 1 to the power of m. This is an m to the power of m, and then t to the power of m. Good. Let's take the product of these two expressions. So if we take the product, we get exponential x over 2. So let's factor out x over 2 here in the exponent, and then we just need to sum this thing and that thing. But the good news is that all of these terms will cancel. So we get exponential to the power of 0. That's 1. And that's obviously the one that we're after for the right-hand side here. So it looks like we're on the right track. And then on the right-hand side, we have a product of two series expansions, m and n running from minus infinity to plus infinity rather, Bessel function of order n, Bessel function of order m, minus 1 to the power of m, t to the power of n plus m. So pause the video and try and collect like powers of t in order to prove that equation over here. The substitution we need to do is obviously n plus m equal to k. So m plus n equal to k. And let's use our favorite diagram to try and figure out what happens with the summation limits here. So if this is the m-axis and that is the n-axis, then every cross in this diagram just corresponds to a single term in the series expansion, in the product of the series expansions rather. So this time m and n run from minus infinity to plus infinity. So I have a lot of work here. Okay, let's stop here. Let's try and figure out where do we have in this diagram all the crosses that correspond to a given value of k. So let's focus first on k equal to 0. So we get k equal to 0 when m is actually equal to minus n. So that's just going to be this diagonal line here. So over here, k is equal to 0. Then over there, we have a line where k is equal to 1. That's right, because if we look, for example, here, m is 1 and n is 0, so the sum is 1. And then we have this diagonal line where k is equal to minus 1. So you start seeing the pattern, and it becomes obvious now what the limits are for the sum. So 1 is actually a sum, first of all, over different k values. And it's obvious that k will run all the way from minus infinity to plus infinity. So k minus infinity to plus infinity. And then for a given value of k, we can either keep m or keep n. It doesn't really matter, but in this case, let's just focus on keeping n. So let's see what happens when we look at a given value of k. So at a given line here, what happens to n? For a given line, n actually runs all the way from -infinity to +infinity also. So we have a sum n going from -infinity to +infinity. And now we just rewrite what we had up there. Jnx, jm of x, so m, that becomes k minus n of x, and then -1 to the power of m, so that's k minus n. So these are all the coefficients that correspond to t to the power of k. Okay, let's take stock of where we are. We have a boring left-hand side, which is just a constant, and then we have a power series of t on the right-hand side. This thing needs to be true for all possible values of t. So obviously we can just focus on the coefficient where k is equal to 0 and then the amount that we have equality on both sides. We can also look at higher orders of t, and then the result will be that the coefficient is 0 because there's no other powers of t on the left-hand side here. But in our case, we're interested in the value where k is equal to 0. So in that case, we have 1. So what's the coefficient where k is equal to 0? We have a sum where n is going from -infinity to +infinity of j and x, and then j. So if k is equal to 0, that becomes -nx. And then we have -1 to the power of -n. The good news is that we know that this thing here, thanks to the parity relations of Bessel functions, is just jn of x. So basically what we have here is a sum of squares. So jn squared of x. And now we're basically done looking at what we had here, what we needed to show. That was a summation only involving positive orders. But that's very easy to fix. So let's just split this up into negative orders first. So to sum all of the negative orders, we can have an index that runs from 1 to infinity of then j minus 1 squared. The 0 is special, of course, so we just keep that separate outside of the summation. And then we have another summation for the positive orders, so jn squared of x. Now, if you look at what we had here, this basically tells you that if you take the square of a negative order, that you just have the positive order over here. So this summation and that summation, that's just the same thing in disguise. So we can write down that this is equal to j naught squared of x, and then twice the sum, and going from 1 to infinity, jn squared of x, which is what we needed to show.